Welcome to my new calculus channel. My name is John Gabriel. In today's video, I'm going to be discussing quite a few detailed particulars of the mean value theorem, and I'm going to show you how the mean value theorem is actually what allows you to calculate areas and volumes and hypervolumes in calculus, and that in reality the mean value theorem is the fundamental theorem of calculus. In fact, the FTC, or the fundamental theorem of calculus as known by the mainstream academia, is really derived in one step from the mean value theorem. So what I'd like to show you today is the proper definition of integral as you will see it in the new calculus, but I will still use most of the theorems and methods that you have learned in mainstream calculus, and demonstrate to you some facts which you have never seen published before, nor your professors know anything about, or your math teachers. In fact, your educators are pretty ignorant about the things I'm going to tell you in this video, and I recommend that you pay very careful attention, because even the greatest mathematicians in history did not understand calculus as well as I do. Neither Newton, nor Leibniz, nor Archimedes even came close to the depth of understanding that I have with respect to calculus. So what I'm telling you really is that I know calculus better than anybody else, and you're about to find out in this episode and verify or reject what I've just told you. Well, let's get started. So the way I would define an integral is as follows. Given any particular curve, such as the one you've just seen there, I would find out the average length of all the ordinates in this interval. Okay, I would find the average length of all these ordinates. In other words, the arithmetic mean. So for example, if this is point A and this is point B, then what I'm really looking at is, I'm looking at, first of all, the sum from S equals A to B of F dash, let's say S, all divided by, now remember, you're going to be taking the difference here, which is B minus A, yes? So B minus A, and, well, actually should have put that on the top. B minus A, and you're going to be taking the difference here, which is all the ordinates. So I'm just going to call that n for the time being. It doesn't really matter what n is. It can be 1, 2, 3, 4, 5, etc. It has no effect on the arithmetic mean of all these ordinates, and I'll prove it to you in a few moments, so just bear with me. So really this is the new definition here of the integral, and what we need to do is now figure out a way to calculate these ordinates, noting that we don't really need all the ordinates. So here's what I'm going to do. I'm just going to get rid of all that now for a moment, and do the following. I'm actually able to partition this interval into as many equal subintervals as follows. So for example, let's say I wanted to start with 1, and so I could have one partition, or two partitions, 1, 2, or 3, 1, 2, 3, or 4, 5, etc. I've given myself 10. It doesn't really matter how many partitions you have. it makes no difference to the calculation. I'm just going to leave it at 3 for the time being. And then the values, the ordinate values that I'm going to use are going to be the lengths of these red lines, which are ordinates of the function f dash of x. So I'm going to calculate the arithmetic mean of all those red lines, and that's going to give me the arithmetic mean of all the ordinates in this interval. Now, the reason that arithmetic mean stays the same is that this curve here is continuous and smooth, and I'll tell you a little fact that you haven't heard before. Did you know that if you have let's say a primitive function, something like this, which is x cubed, and if you have to take a tangent line on here, so I'm going to draw a tangent line here at this point, 0.5, right? The gradient of this tangent line is equal to the length of that ordinate, okay? So the gradient of this tangent line is equal to the length of this ordinate, and it's the same for any other tangent line slope in this interval. And this will work not only for this particular curve, but for any curve. It's true, and you've never been told this or heard this before, so let me repeat it for you again. The gradient of this tangent line is equal to the length of this ordinate. Did you get that? Okay, you need to think a bit about that, and it's easy to verify, in fact, but that's one of the things you need to know. So in essence, when we're trying to calculate the arithmetic mean of all these lengths, the only way we can do it, is by replacing each of these values. Let's say this one was f dash, let's say x1, the next one was f dash x2, etc. Replacing all those values with the definition using the primitive function. And I'll show you how to do that. So say, for example, we had the following. We had divided the interval into 3 partitions, okay? So we have 3 partitions, 1, 2, 3, and then we'll use the ordinates in these 3 partitions. So what we're looking at really are these 3 points here. And if we do that, then we need to actually calculate f dash of 0.46825 plus f dash of 0.60123 plus f dash of 0.73434, and divide that by 3. And once we divide that by 3, that will give us the length of the arithmetic mean of the length of all these 3 lines in the interval that we calculate. It's actually all the lines in the interval, because it doesn't matter how many lines there are. And if we multiply that by the interval width, which is 0.4, it will give us the area. Okay, so that's what we need to calculate. And in the applet, the way you see it done is as follows. Let's just move that out of the way now. Okay, so the arithmetic mean is 1.12. And notice that it doesn't matter how many partitions I have. That arithmetic mean never changes in there. The only time it will change is if you move these dots like that, right? Then it changes, but it doesn't matter how many partitions you have in that particular interval. So let's go back to 4, and we'll see that if we're trying to calculate the area, it will always be the arithmetic mean multiplied by the interval width, which is 0.4. So that will give us an area of 0.448. And this ties in very beautifully with the idea that area is the product of 2 averages. So for example, the area of this rectangle is equal to the arithmetic mean of the lengths of all the vertical lines, which is just the height, and the arithmetic mean of all the horizontal lines, which is just the width, and the area is just h times w. And similarly here, the area is just the arithmetic mean times w, which is 0.4. All the horizontal lines, the average of those, and the average of the vertical lines. Remember that all that's really happening here is you're squashing down this area as follows. So you're actually taking, you cut, let's say there's the arithmetic mean there, you're cutting this area off here and forming a rectangle by dumping it in here, so that your new area looks something like that, right? A rectangle. And then it's very easy because you've got the arithmetic mean and you've got the interval width, and hence you have area, which is just height times width. And so we come back to this problem here where we have the three ordinates. It doesn't matter how many you have, but how do we proceed from this step to calculating the actual arithmetic mean? Well, we note that this particular value, well, each of them in fact, is really equal to f of 0.4685. Well, let's write them. It's 0.4 plus 0.4 divided by 3 for 3 intervals, right? We have 3 intervals. So it's 0.4 plus 0.4 divided by 3 minus f of 0.4 divided by, so this is represented by that, right? Similarly, this here is represented by f of 0.4 plus 2 times 0.4 divided by 3 minus f of 0.4 plus 0.4 divided by 3, again divided by the subinterval width. And you'll notice that this cancels out with that, right? So in the end, you're really left with only the two values. This value here that you see, this value that you see here, and this value that you see here. And that's really equivalent to stating the mean value theorem. In other words, f dash of c is equal to f of b minus f of a over b minus a. Okay, and in fact, this is the true mean value theorem. You really are not interested and do not care that there is a c such that f dash of c is equal to this finite difference. That's a non-remarkable fact, and it doesn't really matter. Just imagine if you had a curve that went something like this, yeah, and something like this, and then something like that. This also has a c, but in this case here there is no c such that it's equal to a finite difference. Why? Because this curve here that you see on the right here is continuous, but it's not smooth. Okay, it's not smooth. So the two things that make it possible for this finite difference to work is the fact that the curve must be continuous and smooth, and then this identity is true. Now, from this theorem, we arrive in one step at the fundamental theorem of calculus, and you'll be able to see that in all the other videos on my YouTube. There's one called what is a real mean value theorem, and I'd advise you to look at that one. And there are several others. So the main one is, what does the mean value theorem really say? And it's about 17 minutes long, and it explains everything, but not as in much detail as I've done in this particular presentation. So if we go back here, you'll see that these red lines are actually the means between the m parts of the subintervals, right? So you'll see that this red line is between the purple and this green line, and this red line between the two green lines, and likewise this red line between the green and the purple line. These are submeans. In other words, these means here are means of this interval, this one here, is of this interval, and this one here of the pink and the green line. So that's really how the mean value theorem works. And if we look at these two curves, you'll see that always at this particular point here, where the arrow is pointing, there is a tangent line. The gradient of that tangent line is equal to the length of the red line. Okay, the gradient of the tangent line is equal to the length of the red line. So really, when you're calculating an area, you're finding the product of two arithmetic means. The arithmetic mean of all the vertical lines and all the horizontal lines. And this is something that, unless you understand very carefully, you can never understand how or why calculus works. It doesn't matter how many partial differential equations you can solve, and it doesn't matter how good you are at numerical methods or anything else involving calculus. You do not understand calculus unless you're actually able to understand what I've explained to you in this video. And what I've said here applies everywhere. It applies to every other curve that is continuous and smooth, or as you've heard in the common lingo, differentiable. And that is really all I wanted to show you in this particular video. I hope you've enjoyed it. This is the New Calculus channel. I'm John Gabriel. Till next time, goodbye.